Sherrer Institute. Unfortunately, he cannot be with us. He's joining us by Zoom. So he will talk about creating and tuning electronic states and phases of neodymium nickelate. And when you ask the questions, I will repeat that for them. So, Milan, you're on.
Okay, thank you very much. And as usually at the beginning, but here very specially to say.
We lost. I didn't touch anything.
Personal and business issue, I could not travel to Brazil. I promise I will. And this is going to be a wonderful workshop, and I'm really a bit jealous to not be with your guys there. So let's share something with you, at least, you know, some of my thoughts, some of my results, and to be at least with the voice in room. So today I will ask well, but it is how to tune electronic states and even more, tune the phases in the struggling correlated system, which could be a very good candidate for novel electronic devices in the future, because nickelates in the very large, or let's say big message, they emphasize and they show metal insulator transition, which is pretty high. So the metal insulation transition, you will see later, it is being somewhere close to the room temperature. So whenever you have some big change, platform rises. It will work. Not working now. Why not? Now. In general, how you can electronic and other phases, physical properties in the material which has these perovskite-like blocks, ABO3 system oxide, okay, and the structure. So I could see that this is, you know, distortion of the BO6 octet of the system. So of course, this firstly will influence the energy split in between the D shell bands. And so then immediately you will go, you know, let's say from one band system to the multi-band system and so on. But of course, there is one trivial way. If you just dope any kind of the compounds, you will change the electronic property just because of the simple filling the bands. So you get some change in the conductivities. So there is but subtle change in the system. When you are changing octahedral rotation, then binding angle will change. Then you will influence the hopping probability, how electrons will hop from the one side to the other, and this.
We can try to switch to a phone connection, perhaps. Is it possible?
If you change octahedral rotation or binding angle. And there is a bit more kind of the system of the effects which are including proximity effect. So if you put your system in close proximity to another system, then you can change the doping just simple because of the charge which will go from one material to another, or more generally speaking, you can transfer orders from one system to another, or to create something new because you put something in the very close proximity. So how to turn those four knobs in general? Of course, defect engineering is one way. So you are inducing defects. Everything of this can happen in some sense, and or altering crystal structure. So that means you use external stimuli, for example, external pressure, and or bending, or twisting your materials. everything of these could happen. And then more kind of something which you can control is the lattice strain. So when you do heteroepitaxial growth of the one material over the substrate, then you can control the. Hello? Yeah.
I'm sorry, we have to interrupt you because the connection is really bad.
Yeah.
Now very choppy, so we try to reconnect again. So I'm sorry for the interruption, but we'll try.
No worries. Did you hear at least something?
Yeah, but it's choppy. So
okay, so you will do something. Yeah, good. Go on.
Just a minute.
Yeah, just.
So maybe everybody can disconnect it from the Wi-Fi so that
we reserve the bandwidth for it.
Yes.
Ah, you reserve bandwidth. Okay, at least I'm speaking about bandwidth.
Otherwise,
And ask him to turn off the video.
Yeah, I will do that.
Yeah, you could turn off the video.
you can turn off your video also.
Yes, I do that. Yeah.
Yeah. So we reserve all the bandwidth for the sound video.
I stop.
I have an hotspot.
Sim, desde ontem.
Não tem a outra.
Não tem. Parece que é fora do prédio. Tentaram resolver e é fora do prédio o problema.
Nobody can provide us an hotspot otherwise.
Mine is not good, so.
But we can ask somebody.
Okay, we try it again now. Shall we try again?
Try again.
Okay, I can go on.
Yeah, go on.
Okay, good. So what I said last, I just repeat last sentence. So how we can turn those 4 knobs, which I put just 4, there are probably many, via defect engineering, altering crystal structure, inducing the lattice strain, for example, growing the one material over the substrate and inducing heteroepitaxial strain, or just proximity again in the multi-layers compound. So let's go with something which it's necessary. Whenever we are talking about, I will do a bit of the advertisement. Whenever we are doing something like that we would like to discover, but really something to discover by creation, you need to have a very high experimental tool, or to be very good in the computation and in the theory to predict something. However, theory and experiment should work side by side, and I'm fully experimental, so I will just show here our experimental toolbox. So for the moment, as you know, I'm working in the last 10 years and more at the Paul Sherrer Institute. This is National Institute of Switzerland, at the synchrotron, Swiss light source, and then one particular beamline which is equipped with a very multiple and complex system for the sample growth and sample characterization, including the tool which uses the synchrotron light for probing electronic structure of the system. So as you can see, what we have here is the PLD system, behind is the MBE system, here is the STM, and then we have this huge, let's say 4 meters transfer line, which we are transferring the sample in the ARPES end station, which we are probing directly electronic properties and electronic structures of the system. So this is Toolbox. So at this beamline, which I'm saying now, we are trying to discover novel properties by creation. So using the systems, using what nature grants us, which means with the elements, then putting them in the kind of the complex structure by the growing, right, with the thin films on other substrates or on other films, and using the spectroscopy, we are aiming to create the new properties and to move toward to the novel quantum materials. This is not all, because we are also trying this is the project which we are in now run. This is to build even more powerful beamline that we will use 2 end stations, one that will be ultra, that we go to the ultimate parameters for the
Continue, Marcelo.
materials that we can probe systems in operando conditions. Of course, everything will be surrounded by this cluster and equipped by this cluster, which is for sample growth and pre-characterization, as STM. So coming back to the topic. So if you are, as I said at the beginning, if you have the system which show phase transformation, this system is already very good candidate for quantum devices. For example, nickelates, we show metal insulator transition, which is what you can see. Here is the paramagnetic metal, and when you are lowering down temperature, you will go, depends on the elements which are there, you will go to the charge ordered paramagnetic insulator or charge ordered antiferromagnetic insulator. You have very good platform to use it for the potential applications. So what you could see here, this is pretty complex diagram, and you could see this is rare earth element right here in the surrounded by the in nickelate, and then you have the element which support this crystal structure. But what is important parameter is nickelate is the tolerance factor. Tolerance factor basically is the ratio between bonds, which is rare earth oxygen, and nickel oxygen bond. Depends of this ratio.
Yes, depending on the ratio, that you have a phase transition, that's clear. We lost you.
So if the tolerance factor goes to be lower, so you are then changing metal insulator transition very much up. So for something as material as the samarium nickel or compound which contain 50-50 of samarium, neodymium or samarium, you go above room temperature. However, system which is mostly studied is neodymium nickelate, because it's turned out that this system is more stable in the kind of powder crystal form. So because nickelates are very difficult to be synthesized and to be stable at the air conditions. However, what is here is important, that for all of this system, nickel-oxygen bond is under tensile strain. So you have the system which intrinsically has the strain there. So, however, there are some good paper which goes from the beginning in this topic, which you can refer here. What I said before, right? The main parameter which we are now going to explore is the metal insulator transition. You could see how this was going up and down, depends on the rare earth you use to stabilize crystal structure. However, if we now focus on neodymium nickel 03, what I said before, we have the already nickel-oxygen bond under the tensile strain or internal pressure. So now if you use external pressure, you could see that you can further tune metal insulator transition pretty efficiently. So for the system which is at the ambient oxygen pressure, you have the metal insulator around 220 or bit lower. And when you are applying the pressure, you go to the, let's say, 15 kilobars, you are going already below 150 Kelvin of the metal insulator transition. So this is not so big pressure that was actually paper in 93. Now you can go in with even much higher pressure in these pressure cells. However, there is another way, which we said because there is internal pressure. So there is always strain, which you can, or say pressure, that you can do also semi-intrinsically. So if you have the film grown on different substrate, you will be able to induce the stress in the system via epitaxial strain. So if you have neodymium nickelate grown on the LEO substrate, then there is compressive strain of the bonds. So you could see that for the thick film of the 12, relatively thick film of the 12 unit cell, the transition temperature is already very low. So it's 120 Kelvin. If it is, let's say, a relatively thick film of the 30 or 15 unit cell of the film grown on NGO substrate, that will be tensile strain, you have the TC, which is lower than in the single crystal, or let's say the powder crystal form, but this is our 160. So there is big differences between those three systems, right? And we have to understand why it's like that. So here is the kind of the summarizing all of this, what I said now. If you have 30 unit cell, it should be bulk-like. You have different substrate, you could see that there is way to tune metal insulator transition from roughly 70 Kelvin up to almost 200 Kelvin. So 130 Kelvin is the range of the tuning metal insulator transition. But what you could see in these studies, that there is another effect happen, that if you are just looking one material, so that means NGO grown on, nickelate grown on NGO, and you lower the thickness, there is already change, because the system goes from something which shows metal insulator transition to the system which shows to be only insulator for all of this temperature which was measured. So that tells us that there is something happening in the system with the dimensionality crossover. So there is kind of not just strain which can be used to tune electronic property, there is also thickness which can be used to tune electronic property, which you could also see in the similar way on the compressive strain now. So if you look all of this data, there is something to conclude, because I have compressive strain, I have tensile strain, effect looks more or less the same, beside that temperature is different, but effect is there. Lowering the thickness, system goes to be insulator in the both cases. So, of course, this is by the transport, but there is more sophisticated way to look what can happen. Using the unresolved photoemission, you can directly monitor electronic structure of the system. And I will just here bit go in the literature, and then later I will go a bit more in the global view, trying to actually show you what we see. So, if you are looking at then lanthanum nickelate, which should be all of the way metallic, and this is what we call the electron pocket and the gamma point. For 8 unit cell is well defined, so that this means that system is very metallic, very well quasi-particle peak formed here. So you go with the lower thicknesses, there is bit of the subtle change in 3 unit cell. Okay, still system is almost the same metallic, and then you go to the 2 unit cell, there is the change, very drastic change, so that the incoherent parts start to pop up, and the quasi-particle peak seems to be going down, I will show, and then 1 unit cell system is gone. There is no metallic state at the Fermi level. So this is here what you could see. This is quasi-particle peak at the KF, so that means somewhere here. You are taking the cut down in the energy. So the quasi-particle peak drastically was going down when thickness was going down. So telling us that there is something happening with the localization. And in order to prove it, the group here was trying to actually did more analysis, looking eye of regular limit, and seeing that actually localization is still above, even for the insulator. But what really happened, that mean free path calculated from this spectrum, it's very much affected below 5 unit cell of the film thickness. So there is some kind of the crossover above 5 unit cell and below 5 unit cell, which was also seen in the previous studies, but just done by others. Okay, so this was on the lanthanum nickelates. We work on the NdNiO nickelate, we already show metal insulator transition, and we also wanted to understand what happened if we are having this film grown on the 2 different substrates. It means on NGO, which will be tensile strain, on LLO, which will be compressive strain. So for such kind of things, we use our tool, which I showed you before, pulse laser deposition system, directly attached to the RP station at the beam line. Here you could see a read oscillation, which actually tell you how many layers you deposit. And then in the end, you stop. You can say, I have this and this number of the thickness. It was 20 unit cell. Here is the read, which shows ordering of the surface. And here is the lead, which shows also surface post grown and already moved to the RP station. So surface is well ordered, showing orthorhombicity sign, which are those strikes between the main peaks. All right. So the transport shows similar what was reported when we have the 20 unit cell grown on the tensile strain NGO, there is the metal insulator transition, pretty sharp at around 150 Kelvin. When you grow the film on the LAO, there is similar trend, right, in the metallicity. You see, there is the almost overlapping between those curves. And then the metal insulator transition is lowered. But overall, even at low temperature, metallicity here is still kind of there. So the system is not really insulated. So you see, in the NNO grown on NGO, the insulator is shooting up behavior, right? While here it's not. So there's still kind of the way that current goes through the sample. So now what I wanted to say is the electronic structure of all of these systems, which are in that class of material, is composed actually with these cuboids, which are hole-like, and then you have in the middle of the gamma point you have some kind of the cube, and or let's say maybe globe-like electron-like pockets in the gamma points. So if you do cuts, which we call these cuts, at the gamma point, Fermi surface will look as the circle almost. And when you do this at the Z point, here will be the Z point in the Brillouin zone, the Fermi surface will look like kind, you know, on this crossy-like structure. We did measurement of this both films. So you see tensile strain. We did this at the 90 electron volt. Good things when you are having the ARPS at the synchrotron, it's that you can choose right photon energy to probe the Brillouin zone at the right space position. So here it is gamma point. You could see these rounding things. And this is kind of the sign of the cuboid due to KZ broadening. Just, you know, kind of the spectral weight which leaks out because of not defined well KZ positions. While at the 65, we are then in the AZR plane, you could see this, what we call this crossy-like Fermi surfaces. So, all right, everything what was calculated, we could see. So, very good agreement. And then this is done at the 200 Kelvin when system is clearly metallic. So another film, which is NNO grown on the compressively strained LAO, right? So we also see this kind of the round things at the gamma point and this structure, but it is different, right? Because they are much like pockets are bigger compared to this one, and what other things happen at the A point, we see sign on another round pocket. So this was a bit surprise for us to seeing that system actually went through the very strong alteration of the Fermi surfaces. So the topology of the Fermi surfaces changed a lot. So it is not just that this is, you know, kind of small change. So having another Fermi surface, it's the charge balance is very different in those two systems. So a bit more, what happened when we are cooling down sample, right? When we go, I'm now just in the plane which is Z, so the ARZ plane. So this Fermi surface should look like that. You can see. So when we are cooling down, it is insulated. There is no Fermi surface to be measured at the 20 Kelvin. This distance you could see how big is here, while you are having the IRZ system here at the 20 Kelvin, you could still measure. So the sign of the Fermi surface is still there. Of course, spectral weight is lower, but Fermi for at A point is the kind of the round things. Usually it's always like that. In order to understand what we are doing, right, we need the calculation. And this is our collaborators calculated that, and what we got is the really very good agreement with the experiment. So this band, which is hole-like at A point, when you have tensile strain, staying pretty much below the Fermi energy. So it's something about 200-300 millielectron volts below. once you have the system compressively strained, Fermi energy, and forming the new Fermi surfaces. Beside that, there is also change of the KF position of that band. So this momentum-dependent density fluctuation calculation actually shows very good agreement and explanation for this kind of the alteration and the modification of the Fermi surface. So this is this new pocket which is now at the zone boundary. So summarize this first part of my talk. So NNO over NGO under tensile strain, right? So what happened there? Because I said at the beginning that the system, even without any stimuli, nickelates are strained and tensile strain. Nickel-oxygen bond is tensile strain. So if you induce additional strain, the reduction of the MIT will occur. So this is 150 Kelvin compared to 200 Kelvin at the room temperature. Electronic structure roughly the same as calculated for the unstrained system. Whatever happened with the compressive strain is much more. So it significantly reduces MIT, something about 50 Kelvin or say below 100 Kelvin. Electronic structure is much different than calculated for the unstrained system. Of course, what happened with is right, the TG orbitals are lowered, TG orbitals are lifted up, and as consequence, the new pole-like Fermi surface at A point is formed. So this is our work, which was in 2015, and we think that with this way we close what really strain can give us in the MIT picture. And if you see now, right, this is this phase diagram which I showed before, a bit simplified. So the strain basically moves the system in the way to be more metallic or paramagnetic metallic or insulator. So you are able to move that line in and out. So because you are changing the basically tolerance factor by the heteroepitaxial strain, sorry. But why we are not trying, sorry? Yeah, so why we are not trying to do something more, to change also this magnetic line and separation line. For that, we actually use the buffer layer, magnetic. We grow nickelate film, which is now ultra thin, over the LSMO, which is antiferromagnetic, or LCMO, which is antiferromagnetic. You could see in the transport, there is drastic change, depends what you put below. If system is unbuffered, it's insulator. If system is on the, let's say, for example, on ferromagnetic layer, is almost metallic all of the way. For studying magnetism, there are several methods, but for example, screed. But screed is problematic because screed is probing everything, probing the substrate, probing the buffer layer, probing the film is not easy. For such kind of the very sensitive system, we are using also secreton-based technique, which is XMCD. So our XMCD shows that the system, as manganese, is showing ferromagnetic loop, but also nickel shows XMCD signal. Of course, much smaller because it's 10 to minus 3. Here is let's say 20 level. Here is the level of the 1, 2, 3. So there is the ferromagnetic sign in nickel. If you are looking how happened everything with the temperature, so this is ferromagnetic moment of the LSMO, which actually shows the ferromagnetic paramagnetic transition at 280. You could see, but it's interestingly. Ferromagnetic moment in nickel is following that line, showing also this trend. So that means they are locked together. Of course, in the ARPES, how to see magnetic ARPES is not easy. So we also look over the old temperature strain and look in the spectral weight. What is spectral weight that quasi-particle stays all the time down to the very low temperature, showing that system preserved to be metallic, as also transport says. So the system is metallic and ferromagnetic. In order to also model the system, we use the same momentum-dependent density fluctuation modeling. And what we could see here that paramagnetic states, you could see this band here, right? When it's ferromagnetic states, there is bit of the change of the redistribution of the spectral wave, while antiferromagnetic will open the gap. So here I will ask you to pay attention. This is cut and or RA cut. So there is basically more or less similar things. Here is the bit of the shifting of the band down, while on the antiferromagnetic is open. So if I'm looking now paramagnetic, spectral wave at the Fermi level, or ferromagnetic, you could see there is the redistribution of the spectral wave, and in the experiment of the very low energy, or let's say close to the Fermi level, we see this kind of the shift. So red is up, green is down. Red is up, green is down. So experiment and theory goes well together. And so for the last slide, I would like just to summarize. So we are strained, we are able to alter electronic states for the Fermi surfaces, and with the buffer layer, we are actually showing that there is possible to create new phase, because neodymium nickel is not ferromagnetic, but we are able to show that there is induced ferromagnetism via buffer layer. And for the last slide, many thanks goes to my collaborators. There are 3 guys, especially I have to acknowledge them for this work. This is Professor Dhaka, now professor in India. Marco Caputo, beamline scientist, will take charge of the beamline at the Max 4 in Sweden. And Zoran Ristis, professor now at Belgrade University. And with that, I'm finishing, and thank you very much for attention. And again, sorry to not be with you.
Thank you, Milan, very much for this talk. We now may have some questions.
Hello, thank you for the talk. I would like to ask, how do you assess, measure, or estimate the percentage of strain? And also, how is it included in the calculations?
Can you please repeat? I didn't really hear.
I'll try to repeat.
It's 2 questions.
Yeah, there are 2 questions. First one is how you estimate the amount of strain, and the other is how you include that in your calculations.
Yes.
Yeah. Okay. Right. So the amount of the strain is estimated by the XRD measurements, by the diffraction, and we actually input exactly that value, which might not be completely, correct, but turn out to be close. Means that we can see effect of the strain in the calculation. So this is the parameter which we use for the calculation from the experiments.
Okay, thanks.
Go in front of the computer. They can go to the computer. Yes. But still with the microphone. So now I have 2 microphones. Yeah, now we have to go to the computer. So I thank you for the talk. I have 2 simple questions.
I'm sorry, I also cannot tell, yeah.
Yeah. How much strain can the system handle? How much you can put? And is it possible to grow this on piezoelectric substrates like PZT and force
yes.
to tweak the thing?
Yes, that's actually great idea for the next step. Is exactly to have something which can continuously change the strain, which could be kind of the piezoelectric buffer layer. I like what you said now. Yes.
And how much strain can it handle? Do you know?
Usually what, let's say by my experience, I can tell you. So the system can be up to, let's say, 3 to 4% pretty stable, to not crack of the energy which are input by the strain. And more, it will probably relax immediately. So you will not be able to complete. but up to 4%, it shows, system usually shows that they can sustain that amount of strain.
Okay. We have another question. Hold on.
Okay, so these nickelates are supposed to be multiferroics, right? And so you made one of them become a ferromagnetic. So should you expect some change in the connection between ferroelectricity and magnetism in that case, or have you any idea about that?
Chairman, can you repeat, please? I mean, I didn't really. I'm sorry.
So
I didn't get. Oh.
Go there.
I'm really sorry, guys. Yeah.
No, I think it's the microphone. Sorry.
And now I can hear better.
The question is, these nickelates are supposed to be multiferroics, right? Some of them. And here you have
Some of them.
changed, yeah, you have changed the antiferromagnetic phase to a ferromagnetic phase, putting this on another
Right.
layer. And do you know if there is some change in this multiferroicity or any change in the dielectric polarization connected to this?
No, I don't. We didn't measure that. This would be also very, very great. The set of the data which can better explain what means this new phase.
Okay, small question: do you have a single crystals for this case, or only power?
No, so that is actually challenging because neodymium, any nickelates, it's enormously difficult to be synthesized in anything bigger than couple of the 100 microns. And that, for any measurement which are related, that you need to do precise transport measurement to put the contact, etc., is enormously difficult. So this is why when you are having thin film forms, volume is still small, right? Because we have something which is 20, 30 nanometers thick, but surface is big. So you can do many things on that surface. Welcome.
Some more questions? Yeah. Or maybe, yeah.
Hi, Milan. Thank you for the
Hello.
talk. So the NNO is very sensitive to the substrate, right? The physics depends a lot because of the strain, exactly. Have you tried to grow NGO, NNO, and LSMO and measuring LSMO above the NNO and see if that changes?
Yes. I mean, I was a bit, sorry that I could not put everything like that. Yes, exactly. Because there is change in LSMO as well. Because, all of this interaction, whatever happened, so let's see a couple of slides. TC about 280.
Okay.
So lately grown. So that means there is.
Oh, Milan, you're choking. Your video.
So there is. There is, of course, change in the another layer as well. And we have the XMCD done also on that layer. But I agree, that could be very interesting to look.
Yeah, could be very interesting. You do agree?
Our focus of those projects have been actually nickelates.
Oh, Milan, sorry, the video crashed and the audio. Can you turn off your camera?
Yeah, sorry, I will. Yeah.
Okay. And repeat, please. I couldn't understand.
Yeah. So what I said. If you are looking this set of the data, in XMCD set of the data in this bilayer, LSMO, so in manganese, shows the transition at 280. When it is just LSMO with the same thickness, grown on NGO, this TC is about 320, 340. So there is the exchange, kind of the exchange bias on the LSMO side as well. And as you have been now suggesting, it will be also important to go in details to see what happened in the LSMO side as well. We have the paper which we look LSMO, but not in the contact with NNO. We look this LSMO in the contact on the strontium ruthenate, seeing how buffer layer can alter and change magnetic properties of LSMO. There is something actually interesting, and I'm quite sure that if someone wants to go in this direction, here will be very interesting physics to look for.
Okay, thank you, Milan.
Thank you.
Maybe we have time for one more question. Okay, so I'll ask you something. In the previous transparency, where you do the compressive strain on LAO, you lower your metal insulator transition to 100 or 50, but then you show RPS at 20, and there is no much change, but the system is supposed to be an insulator. Do you understand?
Actually, no, because you see in the transport, it's not insulator, because you could see this is around 20 Kelvin. So the resistance is not so high. So
Yeah,
you see this is.
But it is going high. It's going up. So normally when the resistance goes up and you lower the temperature, you expect that some sort of gap
Because
is taking place.
usually, yeah, because this current can still go through. And then if I go to the, so if I go now here, right. So it's true that the spectral weight here is much lower compared to here. You could see. So that means the correlation is increasing, quasi-particle weight is decreasing. So that means that there is the change toward to insulator. The system is not yet insulator. Maybe it, will be insulator at 5 Kelvin completely.
But why the resistivity is going up?
Because the localization is increasing. So there is effect of localization by sure. We see this by RPS. So the spectral weight, you could see this is weak spectral weight. Fermi surface is existing, but compare here, which is much stronger spectral weight than here.
Okay. So the claim from RPS is that you only see lower spectral weight.
Yes. I mean, I can just go bit like that. Look at this. That is what happened basically in the metal insulator transition. So the spectral weight goes down. You see, spectral weight goes down, but the Fermi edge is still there. So there is kind of you see, and the mean free path goes also down in some sense. Spectral weight in the of course this is lanthanum nickel, but it's similar effect with the temperature. So the spectral weight is redistributed, system goes toward to insulator behavior because conductivity is much lower, but still not yet insulator.
Okay. No, I'm asking because the form of the resistivity looks very similar to what we observe in dynamic and mean field theory calculations of a metal to an correlated antiferromagnet. And I understand that this system is an antiferromagnetic in its...
Yes.
So...
Yes. So let's say what also there are something in the literature, very good discussion. So in the literature is this kind of the metal insulator transition, right, is happening in the way that is not at the same time everywhere in the system, right? So you have the system which are still maybe metallic, some of them are less or more metallic, and some of the less they're already insulator. In the RPS we are averaging those domains, and we see that maybe just in the spectral weight how this goes down. This is one of the explanation. In the resistivity, until all of these patches goes to insulator, you will not have them to be total insulator. It will of course increase resistivity, but it will not yet turn to be complete insulator.
I see. Very good. So we will thank Milan again for his talk.
Thank
Milan.
you very much, everyone.
Yeah. So we move on. So we will disconnect. Should I disconnect? Say bye bye. Bye bye, Milan.